Prakash, can you explain why this project is important?
Well, most sugarcane crop in Australia and globally are rain-fed or supplementary irrigated, and because of that they experience periods of water deficit during crop production and consequently crop loss. For example, in Australia alone, the sugarcane crop loss due to water deficit is estimated to be around $260 million annually. So just because of that economic loss itself, producing sugarcane that are more productive under water deficit will have substantial economic benefit to both growers and millers.
It's been going since 2007. What have we learnt so far?
Well, I guess we've learned a lot of things about how sugarcane responds to water stress, but probably one of the more interesting things, and one of the things that's got possibly a lot of practical application to our breeding programs, is that we found that the stomatal conductance, when we measure cane even at this early stage, around October or September, that if you look at the correlation between the conductance across a lot of genotypes and correlate that with the yield, the mean yield across a whole range of environments, the combination of the conductance measurement and an estimate of the leaf area has a pretty high correlation with the mean yield. And that's a very interesting result. We think that's probably because the varieties that have got more vigour, that have a higher photosynthesis rate, drives the stomata open, and that we're picking up just basically clones that are more vigorous and at a very early stage. The practical application of that is that we think that we might be able to screen clones at an early stage when they're about this size, before there's any competition between the different varieties, and if we can upscale that sort of measurement in an early stage trial in a breeding program, that could offer us a lot of gains for the early stages of selection. Because at the moment we know that the early stages of selection is quite ineffective mainly because of interplot competition. There are technologies that people are using in cotton and wheat to measure large numbers of plots through imaging. So we think we can do some imaging, detect both the temperature of these leaves, which reflects the stomatal conductance, plus the leaf area, and use that as an index for selection, which could really revolutionise our early stage of selection if that correlation holds up with those measurements. So that's probably one of the more interesting results that's coming out, that we would like to follow up on and turn into a practical application in breeding programs.
So we're standing in one of our field trials here at SRA Burdekin. Can you explain what's actually happening in the field here?
Yes, Marian. Here we have 20 varieties, 10 varieties from the best varieties selected from the breeding program, and 10 varieties we selected based on the physiological mechanisms for drought adaptation. And we have 3 water regimes: fully irrigated, half irrigated, and completely rain-fed conditions. And now we are looking at the mechanisms which confer drought tolerance, and we want to pick up the best clone which can survive better under drought conditions or rain-fed conditions. And also we want to pick up the best clone which have more water use efficiency, which can save a lot of water under irrigation systems.
Okay. And you've got another trial, is a pot experiment. Can you tell us about that one? Yes,
Marian. We have one big trial at SIP in Townsville. We are looking at the more detailed physiological mechanisms, and we are trying to test those clones under high carbon dioxide and high temperature conditions. That main aim is to look at the best clones which we can keep for future climate change, which we expect high elevated carbon dioxide and high temperature, and we think that the sugarcane clones can survive better under high carbon dioxide conditions and high temperature conditions.